All right, welcome to our AP review number 2. We're going to be talking about the theory of calculus, the IVT, MVT, and EVT. Before we get there, I do want to quickly overview homework for a break. It looks like a lot. Please read it, and I'll be posting updates on my website and things too. But by Friday, April 10th, you need to complete the homework FRQs for AP review number 2. Correct them using the instructions on my website as we've done before and fill out the score report. Over spring break, there will be a 45-minute practice exam that I will email you. FRQ only, non-calculator. You'll need to have no notes or anything out. Open up the document just once. Time yourself 45 minutes. Show all of your work and then email it back to me. This is, to me, really serious. Um, doing this stuff remotely, I need to know in these kind of benchmark moments about how you're doing on a broad range of skills, so I know what we need to focus on. This also will replace any benchmark exam grades that if you do better on this one, I'll replace the benchmark exam grades because this is essentially replacing our practice exams I would have normally done. And lastly, you need to complete the AP Review 3, that's derivatives, that's here in this file, by April 12th at 8 p.m. I'll also be having a codename hour if you want to come join me online for that. I'll post details about that and some optional study times because people are giving me some great feedback about wanting some like mini lessons and classes and things. So I'll offer some things over spring break. So stay tuned. Here we go. Some of this may seem like a review from the intervention I ran earlier this week, but I'm trying to choose some also more challenging types of questions about IVT and MVT, okay? Let's do a quick review of some important things to remember. For our intermediate value theorem, we need to make sure a function meets the criteria before we apply it. The criteria is, in this case, there's criterion, there's one, so the function needs to be continuous. The function needs to be continuous on the interval a to b. Okay? That's all it means. What do we need to show? We need to show a starting value of a function and ending value. And then we can prove that the function passes through. We can then prove that the function passes through values from f of a to f of b. All right. We have f of a, and we know the function's continuous. We know that's a. We know over here we have b. And if this function's continuous, it's going to pass through every value from f of a to f of b at least once. Okay? Mean value theorem. Criteria for that, to apply the mean value theorem, is our function needs to be continuous on the closed interval a to b and differentiable on the open interval a to b. What does that mean we can show? We can show then, if those things are true, we can show that the average rate of change, and so you always, for these things, will write down these average rate of change. We can show that the average rate of change on that interval is going to be equal to the derivative of the function somewhere on that interval. Nope, I put the wrong thing. Where C is between A and B, I'm sorry. There we go. So we'll show the average rate of change, the slope formula, and we can use it to prove that there is a derivative that is equal to that average rate of change somewhere on the function. Graphically, as we've seen sketched out before, what this means basically is if we have some function and we find the average rate of change, so across that interval, across the endpoints, there's got to be at least one place where the derivative value, we usually call that C here, where the derivative value is equal to the slope of the secant line. So the slope of the tangent line is going to be equal to the slope of the secant line. For the extreme value theorem, basically what it says is that if you have some continuous function, we're looking at the extreme value theorem, that if we have some continuous function on some closed interval, so it's continuous on some closed interval, then what do we know? We can show that f of x has a maximum and a minimum at least once. That f of x attains a max and min value at least once. This one's kind of one of the obvious kind of theorems where it's like, if we have some continuous function, then our function is going to hit a maximum and minimum value at least once if it's a continuous function. All right, let's work on applying these and thinking about them a little more. All right, let's take a look at this one. The function f is continuous for -2 is less than or equal to x is less than or equal to 2. And f of -2 equals f of 2, which is 0. And there is no c where -2 to 2, for which f prime of c is equal to 0, which the following statements must be true. Okay, so what do we have kind of as our setup here? We know the function's continuous. So that's good for the MVT, IVT, and EVT. It's continuous. We also know that f of -2 is 0 and f of 2 is 0. But it says there is no c on that interval where the derivative equals 0. They're talking to me about a derivative. That immediately cues in my mind, this sounds like an MVT. But they're saying there's no c. MVT should be able to prove there is a c where the derivative is 0. Why? Ooh, I didn't finish writing my 0. Should be able to prove that there is a place where the derivative is 0 because, look, on this interval, if we do if we find the slope of the secant line, we would have f of 2 minus f of -2 over 2 minus -2. Well, f of 2 is 0, f of -2 is 0, so this will give us 0. So there should be a place where the derivative is 0, but we're saying there is no c where the derivative is 0, so which must be true? Well, if there's not going to be a place where the derivative is 0, does that mean that the derivative is greater than 0? Not necessarily, because if we want to start and end at the same y value, you could have like a corner or something and then come back down or whatever. So it doesn't necessarily mean that the derivative is greater than 0. It doesn't necessarily mean that the derivative is less than 0 for this whole function. We're not actually told it's differentiable, so this corner kind of situation would be possible. It says for that interval, f prime of k exists. Not necessarily. We're not actually even told that this function is differentiable, so we don't necessarily know the derivative exists. For that interval, f prime of k exists, but f prime is not continuous. Not necessarily, because if we do have a corner situation or something, then f prime of k wouldn't exist. So that one's not going to be there. That's not going to be a possibility for us. So we're left with E. For some k on that interval, that means the derivative does not exist. That is what must be true. Because in order for us to start and end at the same point, same y value, the only way to make that happen would be for there to be some place where the derivative does not exist. If we're going to start and end at the same value, but there is not a place where the derivative overall is 0. So this is kind of a sneakier MVT question. Let's take a look at the next one. The derivative g prime of a function g is continuous and it has exactly 2 zeros. Exactly 2 zeros. Selected values of g prime are given in the table above. If the domain of g is the set of all real numbers and g is decreasing, then g is decreasing on which of the following intervals. So let's just write ourselves a note here. G is decreasing. That means we want g prime to be less than 0, right? If g is decreasing, the derivative is 0. We have these points up here. For some of these table problems, it's kind of nice to just visualize stuff. So let's just kind of like plot out what we might know. That is probably much longer than I need that axis to be. So when x is -4, we kind of go 2, 3, then we have 0, -3, -2, -1, 0, 3. Oh, did I get? I'm 2, 3. I'm sorry. Oh my goodness. Oh my goodness. I am making all kinds of things. Let's back up for a second. All right. The derivative of g here is shown, and we're told that g prime has values given up here. So what I was graphing there, if I can go forward again, I was graphing there, these points are actually points on g prime, right, of x, the derivative values. And if I keep going, I would have a derivative value at 3. Oops, sorry, 3 would probably be a little higher than that, given what I put over there. At 3, and at 2 again. So my derivative graph does something like this. I don't actually know that it's differentiable, so I'm just going to kind of go through and make a vague possibility of a thing. Okay. So here's what I know. I know that g prime has these points, and I know it only has 2 zeros, so how can I connect things like this? Well, I know that it has exactly 2 zeros, so I know, no matter what happens, that my g prime graph crosses here and here, right? So if my g prime graph crosses here and here only, what do I know then about g prime of x? Because g prime has only 2 zeros. G prime only has 2 zeros here, right? I'm looking for where g prime is going to be less than 0. So if I know that g prime has exactly 2 zeros, then if it crosses here and here, at x is -2 and x is +2, then on the interval -2 to +2, then that means that my derivative is negative. Because if I only have 2 zeros, on this interval is the only time then when g prime is going to be negative, because the rest of it has to stay above the x-axis, no matter what it does up here, right? So my correct answer here would be A. You might go, how does this connect with the theorems, MVT, IVT, those things like that? Not necessarily directly, but this kind of reasoning about, hey, we only have 2 zeros. We only have 2 zeros here. So we have to know some sort of elements of the behavior of this graph, that we're going to have to start positive and pass through all the values to get down to 0. And then we're over here at 0 again. That's our only other 0 on our derivative. So we have to pass through values that are negative to get back over here, meaning that this interval, -2 to 2, is the only interval on which our derivative is going to be negative. Sorry about the few hiccups there. All right. Let's take a look at a free response question that had to do with some of our MVT, IVT stuff. I've also thrown some other review questions in here as well. Good practice, right? Okay. So we have a situation. We got concert tickets being put on sale at noon. We are sold, and they were sold out within 9 hours. The number of people waiting in line to purchase tickets at time t is modeled by a twice differentiable function L of t up here. It's twice differentiable. The values of L of t at various times are shown up here. If you want to, please go ahead, pause the video, try these two parts, and then come back and check it. If you want an example, I'll go ahead and move through it now. All right. Part A, use the data in the table to estimate the rate at which the number of people, we want to estimate the rate at which the number of people waiting in line was changing at t equals 5.5. Estimate a rate of change. When I see that phrase, rate of change, ROC, I'm immediately thinking in my mind, derivative, right? Derivative, slope. So t equals 5.5. How am I going to estimate? The L of t is measuring the number of people in line, right? I want to estimate the rate of change, the slope of that at 5.5. That's somewhere in here, right? Somewhere in the middle between t is 4 and t equals 7. So I can say, okay, well, let me take, not f, it's going to be L, isn't it? L of 7 minus L of 4 over 7 minus 4. And let me see what I get. It says indicate units in my answer too, so I'll do that. L of 7 is what, 150 minus L of 4 is 126 over 7 minus 4 is 3. What are my units for 150 and 126? It's people. What are my units for this down here? 7 minus 4, that's hours. So I can actually leave it like this. Would be a fine way to leave your answer. If you do want to simplify and reduce this down, then our value comes down to be 8 people per hour. All right, not an IVT, MVT kind of question. C, for 0 to 9, what is the fewest number of times? What is the fewest number of times at which L prime of t must equal 0? Give a reason for your answer. Now, this question is an interesting one. We know this might have something to do with some of our theorems because they're asking us about a derivative. We know some things about a function, but not its derivative. But this question I chose because it is slightly more complicated in how maybe we can reason through this. Intuitively, what do we know about L? We know that L increases. We can see L increases at least somewhere on this interval 0 to 3. And then it decreases somewhere 3 to 4. And then it increases again. And then it decreases again. So just kind of in our minds, what do we see happen? It looks like at a minimum, L of t increases, and then it decreases, and then it increases, and then it decreases. So it looks like if we just kind of answer this, how many was the fewest number of times that L prime of t must be 0? Well, that's the slope of this graph. It looks like 1, 2, 3. But we need a rigorous way to prove that, right? We need a rigorous way to prove that. We can tell from the numbers it goes up, then it comes down, then it goes up, then it goes down at a minimum. So here's how I think we should best approach this. We do know that L of t is twice differentiable. So we do know, we can go ahead and say that L is differentiable. This lets us use both the MVT and the IVT if we want to, right? So we can say, so the MVT applies, just so they know what our kind of thinking is. Now let's see, if the MVT applies, we could say, okay, so what do we know about this first interval? For this first interval, if I could say f of 3 minus f of 0 over 3 minus 0. I'm not even going to worry too much about the number, but if I found that slope, it would be greater than 0. So L prime of t is greater than 0 somewhere on the interval 0 to 3, right? What else do I know? I can also say, well, what other interval does it look like I have some increasing thing? I could say f of 7 minus f of 4 over 7 minus 4, right, is going to be greater than 0. So L prime of t is greater than 0 somewhere on the interval 4 to 7. Right? I can show those two things pretty quickly. Basically, I took the secant line across 0 to 3 and 4 to 7 to show that, hey, there's got to be a place where the derivative is positive. Right? What else can I show? So I basically showed that I have an increasing section and an increasing section. Let me show my decreasing sections. I can kind of do the same thing. I can say then, okay, f of 4 minus f of 3 over 4 minus 3, if I found the slope across this interval, I would find that it's negative. So L prime of t is less than 0 somewhere on 3 to 4. What else can I know? Okay, so I showed this decreasing interval here. What other decreasing interval do I have? 7 to 9. I can also say, okay, f of 9 minus f of 7 over 9 minus 7, my slope over here, is also going to be less than 0. So L prime of t is less than 0 somewhere on 7 to 9. So basically I've stated out in math language what we pointed out up here. We have some interval where we're increasing, some interval where we're increasing, and then decreasing intervals kind of splitting those, right? Okay. Now let's put this together then. How can we make this conclusion? I can say since L prime of t is continuous, and I know it is because I know that L is twice differentiable. Since L prime of t is continuous, what do I know? I know basically that I go from positive slopes to negative slopes to positive slopes to negative slopes. That sounds like an IVT thing now. Since L prime of t is continuous, the IVT guarantees at least 3 times on 0 to 9 when L prime of t equals 0. If you want kind of to reiterate this, basically what we showed that L prime of t goes from positive to negative, goes from positive to negative, back to positive, and then back to negative, and then so we did that with our MVT, and then we used the IVT to say we have to have a 0, 1, 2, ooh, I wrote a 0 there instead of a negative, and then back to negative. So we have to have zeros in the L prime at least 3 times. Now you can't just kind of do this visual route. We have to go through showing the actual math behind it. Another route you could have gotten into this is if you're really, really careful with your language, you could talk about how we know this function is continuous, and we have, considering it looks like we'd have 3 relative extrema on here, but you have to be careful with your language and talk about the right continuity and differentiability. All right, there's a little tricky one, and then another kind of tricky one. I'm trying to draw our attention to the more challenging ones as opposed to the ones that were in the intervention. Remember, the intervention ones, you can always go to the video that I posted about limits and continuity. The Theora calculus intervention. All right, let's look at another kind of challenging one from a different year. Let's say we have a continuous function f that is defined on the closed interval -4 to 6. The graph of f consists of a line segment and a curve. They don't tell us much about it, except that it's tangent to the x-axis at x equals 3. If it's tangent to the x-axis, that probably means we have a relative minimum there. As shown in the figure above, on the interval 0 to 6, the function is twice differentiable, probably going to be useful for us. And we know that f double prime of x is greater than 0. That's on 0 to 6, right? Okay. For how many values of a, where a is somewhere, some x value between -4 and 6. So what makes this one kind of funky. For how many values of a, where a is between -4 and 6, is the average rate of change of f on the interval a to 6 equal to 0? Give a reason for your answer. Well, even if a question like this seems more complicated, let's recognize certain things that we do know. Average rate of change on the interval a to 6. Let me just write down what that would be, right? Average rate of change on a to 6. That'd be f of 6 minus f of a over 6 minus a. And we want to know how many times is this average rate of change, because that's what our average rate of change means. It's the slope of the secant line. How many times is that average rate of change equal to 0? So I'm just going to write that out. In fact, you get 1 point just for writing this out, okay? So this is why recognizing certain phrases and just writing down what it means is really important. Don't worry about necessarily how to solve it, because then you can start processing like we're about to do. Okay, we want to know how many times is the average rate of change going to be equal to 0? Well, if I think for a second, well, what's it going to take to make this average rate of change equal to 0? The only thing that will make this equal to 0 is if f of 6 minus f of a equals 0, right? That the numerator is 0. What does that mean for us? Well, that means that f of 6 would have to equal f of a. So let me go to my graph. What is f of 6? F of 6 is 1. That's what it says in my graph. So what do I want to know? I want to know how many values of a is it that f of whatever that value is 1. Well, the y value is 1, like right here, right? So how many values, how many a values, remember a is some x value, how many x values in here is f of that x value going to be 1? It looks like 1, 2 times. So f of a equals 1 twice. All right. And it says to give a reason for your answer. Showing this work is our reason for our answer. All you had to say was there are 2 values of a for which this is true by showing these steps. Twice 2 values of a. Okay. So that was part B. So let's take a look at part C. Hopefully I can cram it in down here. All right. Part C. Is there a value of a on that interval for which the mean value theorem applied to the interval guarantees a value of a, guarantees a value c somewhere between a and 6, such that the derivative is 1/3. So they're cueing us to use the mean value theorem, right? Okay. I know for my mean value theorem, criteria-wise, I need to make sure that I'm dealing with something that is continuous and differentiable, right? And this is sort of our key lever into this more difficult question. I need to make sure it's continuous and differentiable. If I'm dealing with the interval a to 6, and a can be anywhere from like -4 to 6, but 6 is definitely included here. I need intervals that are going to be continuous and differentiable. Well, I have a corner here, so I can't choose a starting point anywhere over here, because if I go from like -3 to 6, I have a part of my function that would not be differentiable. So my interval for a has to start at least just on the other side of 0, right? Or at 0, we could say. So I at least need to start thinking over here. So f of a, basically what does the mean value theorem say then if we want to guarantee there's a value where the derivative is 1/3? What we'd be saying is this. Remember, we have to establish our criteria, and then we need to write out our slope over secant line. What does it mean? F of 6 minus f of a over 6 minus a has to equal, I'm looking for 1/3, right? And I know that a, because I can't have a corner or anything, has to be 0 or greater. Now let's think for a second. I want the slope of the secant line to be positive 1/3. So if I started here and did my secant line, I have negative values. So I at least need to be, well, if I had like a point here, that'd be a slope of a secant line. If a was like 1-ish or whatever that is, slope of a secant line would be 0. So I need to be somewhere in the x values over here so that whatever my slope of my secant line is, whatever point I'm starting at, is going to be positive 1/3. And this is where we got to be play around with some things and maybe even use some context clues here. But the only point we really know that they told us about is this one right here, right? If we know the graph of f is tangent to the x-axis, we know that that point has to be the point 30. Well, let's just try that. Let's try the point 30 as our a value. So that'd be when a is 3, right? So let's just try this. F of 6 minus f of 3 over 6 minus 3. F of 6 we know is 1. F of 3 we know is 0. 6 minus 3 is 3. Hey, look at that. We found that the slope of the secant line from x is 3 to x is 1 is 1/3, right? And we know that the function is going to be continuous and differentiable on that interval. So let's write this out. They're asking us, is there a value of a so that the mean value theorem guarantees a derivative of 1/3? Correct answer here is yes. A equals 3. And we can say f is differentiable. F is differentiable on the interval 3 to 6, right? We know that. They tell us that the function f is twice differentiable from 0 to 6. So f is differentiable on 3 to 6 and continuous on the closed interval 3 to 6. We already showed our slope of our secant line, so we don't need to show that again. So we can simply say, therefore, by the MVT, there is a value C, where C is between 3 and 6, such that f prime of C equals 1/3. And this last part I'm really just restating what's down here. They said, is there a value of A? Yes, there is, for which the mean value theorem guarantees a value C so that the derivative at C is 1/3. Yes, there is a value of A, it's 3, because we know f is differentiable and continuous. We showed our secant line, so by the MVT there is a value A or value C between 3 and 6, between these points, such that the derivative is going to be 1/3. Okay. I like that question. It's a little more tricky. That makes you think a little bit harder. All right. Cool. I want you to go ahead and give this one a try. Pause the video, practice it, and then come back and check your work. I've included some other problems to just help you review some other ideas as well. Pause, practice, and then come back and check. All right, let's go ahead and do this. We have a function that's continuous, f. It's defined on the interval -4 to 3. The graph consists of 2 quarter circles and 1 line segment. G of x is this. We always got to be on the lookout for these kind of more complicated accumulation functions. It's 2x, okay? 2x plus the integral from 0 to x of f of t dt. Find g of -3 is the first thing we want, okay? G of -3. Okay, we can try to do that. G of -3 is going to be, I'm just going to plug in x values in for what I know up here in g. 2 times -3, that's going to be -6, plus the integral from 0 to -3 of f of t dt. All right. Integral from 0 to -3. So that's going to be going backwards. It's above the x-axis, but we're going backwards. That's going to be a negative area, valued area. So this is going to be -6. This is a quarter circle, right? It's a quarter circle with a radius of 1, 2, 3. So it's pi, radius is 3, squared is 9, divided by, it's a quarter circle, 4. So I'm going to say -6 minus 9 pi. That's an ugly looking pi. 9 pi over 4. Okay. It says find g prime of x. Okay, g prime of x. I need to take the derivative of the function that I'm given there. That's an accumulation function. G prime of x, derivative of 2x is 2. Can't just lose that. Derivative of 2x is 2. Plus the derivative of this integral will give us the derivative of an integral f of x, right? Antiderivatives and derivatives are inverses, inverse operations there. Will give us f of x, the derivative of the integral. There we go. So we want to use it to find g prime of -3. G prime of -3 then is going to be 2 plus whatever f of -3 is. F of -3, that's going to be a point on this graph, right? Here's f, so f of -3 is 0. So that's 2 plus 0, which is 2. Okay. This was 3 points. 1 point for getting the value of g of -3, 1 point for taking the derivative correctly, and then 1 point for evaluating the derivative of -3 correctly. C, find all the values of x on the interval for which the graph of g has a point of inflection. Give a reason for your answer. Let's just write down our definitions. We can say g has a point of inflection when, we gotta be specific here, when g double prime of x changes sign, right? So that's just our general definition of point of inflection. So let's think about it for this specific problem. What do we know g prime of x is? G prime of x, we already said, was 2 plus f of x. So g double prime of x is going to be f prime of x, right? G double prime of x is just going to be f prime of x. So we can say g double prime of x equals f prime of x changes sign. Okay. F prime, that's the slope of this f graph. So where does our slope change sign? In other words, where does f go from increasing to decreasing or vice versa? The slope of f is positive over up until 0, and then the slope of f is negative after that. So we can say g double prime, which is f prime of x, changes sign at x equals 0. So g has a point of inflection at x equals 0. Here we go. All right, and let's look at part D. So that's only 1 point. You have to get your explanation here right with your answer. And lastly, D. Find the average rate of change of f on the interval -4 to 3. Find the average rate of change of f on the interval -4 to 3. So I can do that. Average rate of change, I recognize that as our slope formula, right? That's a phrase we just got to be able to recognize here. So what do I want? I want f of average rate of change of f. So not my g graph, but or my g function, but f. Average rate of change of f then is f of 3 minus f of -4 over 3 minus 4. What is f of 3? F of 3 is -3. F of -4 is -1. Over 3 minus -4 is 7. So this is going to give me -2/7. Right? So I get 1 point for finding that average rate of change. What else are they asking me? There is no point C from -4 to 3 for which the derivative at C is equal to the average rate of change. So tell me there is no point where there is a derivative that equals this average rate of change. Explain why the statement does not contradict the mean value theorem. Now here's the thing, right? If the mean value theorem is going to guarantee that there is a place, there is a derivative, a place where the derivative equals -2/7, if the mean value theorem is going to guarantee that, we can say for MVT to apply, f of x would need to be continuous and differentiable. I want to save space by not writing out the word, but please write out the words. Continuous and differentiable on -4 to 3. Technically, right, it would need to be continuous on the closed interval and differentiable on the open interval. But to save a little writing here, we'll do this. So f would need to be continuous and differentiable -4 to 3. But what do we have? However, f is not differentiable. One place is actually really obvious. It's definitely not differentiable when x is 0. But it's actually also not differentiable over here. We'd have a vertical tangent line over here where this circle, one quarter circle stops and another quarter circle picks up. So we can say, however, f is not differentiable at x equals -3 and x equals 0. So we say to apply the mean value theorem, f must be differentiable at some point, at each point there on that interval. However, f is not differentiable at x equals -3 and 0. The statement does not contradict the MVT. Now almost 2 points, one for getting your average rate of change and one for stating your explanation for why the statement does not contradict the MVT. Hopefully this helps out, give you a little more clarity and some practice with the MVT, IVT, things like that. We just want to spend a minute to remind you, please make sure you read through the homework, read carefully, and take care of those things over spring break. Stay tuned for some optional study times and codename hour as well. For the spring break practice exam, please follow my instructions and make sure you are following the honor code about that. As we talked about before break, following these kind of practices in college is incredibly important as well. I know we are in strange times, but I need you to do that, okay? Talk to you later.